Imagine a region of space so vast that light takes 1 billion years to cross it. A cosmic desert where galaxies flee from each other at impossible speeds. A void so profound that if our entire observable universe were shrunk to the size of Earth, this emptiness would stretch across the Pacific Ocean. In 2007, astronomers discovered something that shouldn't exist according to our models of cosmic evolution. A hole in the universe nearly 1 billion light-years across, empty, cold, growing. They called it the cold spot, and it violated every principle we thought we understood about how structure forms in space. What if these cosmic voids aren't empty at all? What if they're filled with something we can't see, something that's actively pushing matter away? What if the largest structures in the universe are telling us that everything we know about the fabric of reality is incomplete? Today, we journey through evidence that challenges everything we thought we knew about the architecture of the cosmos. Evidence that suggests the emptiest places in the universe might hold the key to its ultimate fate. Prepare yourselves. We begin. In 2001, the Wilkinson Microwave Anisotropy Probe launched with a singular mission: to map the oldest light in the universe. This ancient radiation, the cosmic microwave background, represents the afterglow of the Big Bang itself, light that has traveled for 13.8 billion years to reach us. Scientists expected to find tiny temperature variations across the sky, ripples that would explain how matter clumped together to form galaxies. What they found matched predictions perfectly, except for one region. In the constellation Eridanus, spanning an area of the sky 70 times the size of the full moon, the data showed something impossible: a cold spot. The temperature there measured 70 microkelvins colder than the surrounding radiation. That might sound insignificant, but in the precisely uniform afterglow of the Big Bang, this represented a massive anomaly. When the European Planck satellite confirmed the finding in 2013 with even higher precision, astronomers faced an uncomfortable truth. This cold spot shouldn't exist. Computer simulations of cosmic evolution produced such an extreme temperature depression in less than 2% of test universes. Something was removing energy from the oldest light in existence. But what? In 2015, a team at the Institute of Astrophysics in the Canary Islands decided to look deeper. Led by astronomer Istvan Saputi, they mapped the three-dimensional distribution of galaxies in the direction of the cold spot. They discovered a void. Not just any void, but a supervoid, spanning 1 billion light-years across and 7 billion light-years away. The data revealed that matter density in this region was 20% lower than the cosmic average. Galaxies weren't merely sparse, they were actively fleeing from this region at velocities exceeding predictions. The integrated Sachs-Wolf effect could explain some of the cooling. As photons climb out of gravitational wells in expanding space, they lose energy. The deeper and faster expanding the void, the more energy the light loses. But here's where conventional explanations started to crumble. The mathematics didn't add up. Even accounting for the integrated Sachs-Wolf effect, this supervoid could only explain about half of the temperature depression observed in the cold spot. Independent analyses from the University of Durham confirmed the discrepancy. Something else was draining energy from this light. The Eridanus supervoid wasn't alone. As astronomers began systematically mapping the three-dimensional structure of the universe using the Sloan Digital Sky Survey, they discovered that emptiness isn't randomly distributed. Cosmic voids form an interconnected network, like the holes in Swiss cheese, with galaxies and galaxy clusters concentrated in thin sheets and filaments between them. The Boötes void, discovered in 1981, spans 330 million light-years. The giant void in Canes Venatici stretches across 1.5 billion light-years. Dozens of supervoids have now been cataloged, each containing far fewer galaxies than statistical predictions allow. These aren't simple empty regions. They're organized structures with specific properties. Voids are more spherical than random chance would produce. They expand faster than the Hubble flow would predict. Matter doesn't just avoid them, it actively evacuates them, as if repelled by an invisible force. In 2016, researchers at the University of Minnesota analyzed the shapes of 24,000 cosmic voids. They found that these structures maintained their shapes over billions of years, despite the chaotic nature of cosmic expansion. Something stabilizes them. The evidence forces us to confront an uncomfortable possibility. These voids aren't passive regions where structure failed to form. They're active structures, shaped by forces we don't fully understand, playing a crucial role in cosmic architecture. But this represents just one piece of a much larger puzzle, hidden in the darkness between galaxies. In 2019, a team using the Kilodegree Survey measured peculiar velocities of galaxies surrounding major supervoids. Peculiar velocity refers to a galaxy's motion relative to the smooth expansion of the universe itself. Standard cosmology predicted these galaxies should move away from void centers at roughly 200 kilometers per second. The observations showed velocities exceeding 600 kilometers per second in some regions, 3 times the predicted speed. Something inside these voids generates repulsive gravity. That's not a metaphor. The mathematics describing void expansion requires a component that acts opposite to ordinary matter and gravity. Consider how cosmic structures typically form. Gravity pulls matter together irregularly, creating asymmetric clumps and filaments. Random processes produce random shapes. Yet voids are remarkably spherical. Analysis of void shapes using the BOSS galaxy survey revealed that supervoids maintain nearly perfect spherical symmetry, even those spanning hundreds of millions of light-years. The probability of this occurring by chance through gravitational collapse and expansion alone is vanishingly small. In 2021, simulations run at the Max Planck Institute for Astrophysics tried to reproduce void shapes using only known physics. They failed. To generate the observed sphericity, the simulations required an additional component, something that fills the voids and pushes uniformly outward in all directions. Cosmic voids aren't completely empty. Sparse populations of galaxies drift through these regions, but they're strange. Galaxies inside voids form stars at rates 50% higher than comparable galaxies in normal density regions. They rotate faster than their mass suggests they should. They're bluer, indicating younger stellar populations, despite existing in regions where matter is scarce. The local void, a relatively small structure, only 150 million light-years across, contains 17 known galaxies. Scientists at the University of Wisconsin-Madison analyzed their properties in 2020. Every single one showed excess angular momentum. They spin too fast for their gravitational mass. Something in these voids affects how galaxies behave. Something that doesn't cluster with matter, doesn't emit light, but exerts force. Step back and observe the largest scale structures. The cosmic web consists of galaxy filaments, clusters, walls, and voids forming a specific pattern. This pattern isn't random. Computer simulations of structure formation predict that voids should occupy roughly 60% of cosmic volume. Observations confirm this with remarkable precision. But here's what the simulations cannot reproduce. The void size distribution follows a power law that extends beyond the largest structures we can observe. This suggests void formation follows a scale-independent process. Whatever creates and maintains voids operates uniformly from tens of millions to billions of light-years, across scales where different physical processes should dominate. The pattern suggests these structures aren't accidents of cosmic evolution. They're fundamental features of space itself. But this represents just one piece of a much larger puzzle. In 1998, observations of distant supernovae revealed that cosmic expansion is accelerating. This required a new component in our equations: dark energy, comprising 68% of the universe's total energy density. Dark energy's properties are bizarre. It doesn't dilute as space expands. It generates repulsive gravity. It's uniformly distributed through space. These are precisely the properties required to explain void behavior. In 2017, researchers at the University of Portsmouth analyzed how cosmic voids expand over time using data spanning 5 billion years of cosmic history. They found that void expansion accelerates at a rate precisely matching dark energy's influence. But there's a critical detail. Voids expand slightly faster than regions of average cosmic density. This shouldn't happen if dark energy is truly uniform, unless dark energy isn't uniform at all. The most remarkable discovery involves what happens at void edges. Where voids meet filaments of galaxies, the expansion rate changes abruptly. Dark energy's influence appears stronger inside voids than outside them, as if voids contain more of this mysterious component. Modern physics recognizes that empty space isn't truly empty. Quantum field theory predicts that the vacuum seethes with virtual particles, constantly popping in and out of existence. These quantum fluctuations carry energy. Calculating the energy density of quantum vacuum fluctuations produces a number that's wrong by 120 orders of magnitude, the worst prediction in physics. This is the cosmological constant problem, and it's directly connected to dark energy's nature. But what if cosmic voids provide a crucial clue? In 2020, theoretical physicists at the Perimeter Institute proposed that quantum vacuum energy might not be uniformly distributed. In regions where matter density drops below a critical threshold, the quantum vacuum could transition to a different state, one with higher vacuum energy. This would cause those regions to expand faster, creating a feedback loop. As voids expand, matter density drops further, potentially triggering additional vacuum energy release. The process would naturally produce spherical structures that expand faster than surrounding space. Laboratory experiments can't test this hypothesis. We can't create billion light-year voids in a lab, but we can observe their signatures. If void expansion correlates with void age and size in specific ways, it would confirm that vacuum energy transitions are real. Initial analysis suggests this correlation exists. Some cosmic voids exceed 1 billion light-years in diameter. Light from the far side of these structures hasn't had time to reach the near side since the Big Bang. This means the two sides of these voids have never been in causal contact. They've never exchanged information. Yet these voids maintain coherent structures. Their expansion rates coordinate. Their shapes remain stable. How does one side of a billion light-year structure know what the other side is doing? String theory and eternal inflation theory suggest a provocative answer. These structures might be imprinted from before the Big Bang itself, during the inflationary epoch, when the entire observable universe expanded from quantum fluctuations. In this view, cosmic voids represent regions where the inflation field varied slightly, creating permanent differences in vacuum energy density. If true, cosmic voids are fossils, preserving information from the universe's first trillionth of a second. They're windows into physics at energy scales we can never reproduce in particle accelerators. The largest known void, the giant void, discovered in 2020, spans approximately 1.8 billion light-years. This raises a disturbing question about cosmic evolution. Standard structure formation theory holds that matter clumped together under gravity over 13.8 billion years. Small fluctuations grew into galaxies, which merged into clusters. Voids formed passively where matter was initially sparse. But gravity can only influence matter within its light cone, the region from which signals have had time to arrive. For the largest voids, their size exceeds what gravity could have evacuated since the Big Bang.
The mathematics is unavoidable. These structures require matter to evacuate faster than standard gravity alone can accomplish. you need an additional repulsive force acting over billion light-year scales, operating for most of cosmic history. The evidence extends beyond mere gravitational effects into the realm of space-time structure itself. What we call voids might be regions where space-time itself has different properties than the regions where galaxies cluster. Three major theoretical frameworks attempt to explain cosmic void behavior, each with profound implications. The first invokes modifications to general relativity at cosmic scales. Physicists like Claudia de Rham at Imperial College London have developed theories where gravity's strength varies with local matter density. In sparse regions, gravity becomes repulsive beyond certain distance scales. This naturally produces void expansion and could eliminate the need for dark energy entirely. The second framework embraces dark energy but allows its density to vary. Quintessence models, developed by Paul Steinhardt at Princeton, propose that dark energy evolves over time and space. Voids represent regions where quintessence has entered a more energetic state, driving faster expansion. The third approach, favored by many cosmologists, including René Chloyek at the Dunlap Institute, maintains standard cosmology but emphasizes that we've underestimated void effects. The integrated Sachs-Wolf effect, combined with weak gravitational lensing around voids, might fully explain observations without requiring new physics. Each theory makes testable predictions. Modified gravity theories predict specific patterns in how galaxies orbit within voids. Quintessence models require the expansion rate to vary with cosmic time in measurable ways. Standard cosmology predicts precise correlations between void size, depth, and their imprint on the cosmic microwave background. Current data doesn't definitively favor any framework. This uncertainty forces us to reconsider fundamental assumptions about gravity, vacuum energy, and cosmic structure formation. Voids exist within voids, forming a fractal-like hierarchy. The local void, containing our cosmic neighborhood, sits within the larger KBC void, named after astronomers Keenan, Barger, and Coe, which spans 2 billion light-years. We live in an underdense region within an even underdenser region. This matters for measuring cosmic expansion. The Hubble constant, the rate at which the universe expands, varies by about 9% between measurements using nearby supernovae versus observations of the cosmic microwave background. This Hubble tension has puzzled cosmologists for a decade. In 2019, a team led by Lucas Lombrisser at the University of Geneva proposed that Earth's location in a cosmic void could explain the discrepancy. If we're in a region expanding slightly faster than the cosmic average, we would measure a higher Hubble constant locally than globally. Subsequent analysis of our void environment by Ben Hoshite at the University of Wisconsin-Madison confirmed we sit in an underdensity extending at least 650 million light-years in all directions. The expansion rate within this region exceeds the cosmic average by 3 to 5%, exactly the amount needed to explain half of the Hubble tension. Our address in the cosmic web directly affects our measurements of fundamental cosmic properties. This raises a profound question. How many of our cosmological observations are local effects rather than universal truths? Voids create an information problem for cosmology. Imagine observing a galaxy 7 billion light-years away, seen through a billion light-year void. That light spent a substantial portion of its journey passing through a radically different space-time environment than we experience. That light carries information not just about the source galaxy, but about everything it encountered along the way. It should encode details about dark energy's nature, modified gravity effects, and vacuum energy transitions. Yet we struggle to decode this information because we don't fully understand how voids affect light. Recent theoretical work by Seshabri Nadathor at the University of Portsmouth suggests that gravitational lensing by voids, negative lensing, where light paths diverge, might systematically bias our measurements of distant supernovae. This could partially explain why different methods for measuring cosmic expansion yield different results. The universe is vast and full of voids. Perhaps 30% of the light reaching our telescopes has passed through significant underdensities. We've been assuming this light provides unbiased cosmic information. That assumption may be wrong. The Vera Rubin Observatory, beginning operations in 2025, will map the entire southern sky every few nights for 10 years. This legacy survey of space and time will catalog billions of galaxies, enabling unprecedented three-dimensional maps of cosmic structure. Specifically for void science, the Rubin Observatory will identify tens of thousands of cosmic voids, tracking their evolution over billions of years. By observing how light from distant quasars traverses these voids, astronomers will measure void expansion rates with 10 times current precision. The European Space Agency's Euclid mission, launched in 2023, focuses specifically on dark energy's properties. Its wide-field surveys will map void shapes and sizes across 10 billion years of cosmic history. If dark energy's density varies between voids and normal regions, Euclid will detect it. Perhaps most intriguingly, the Square Kilometre Array, a radio telescope network spanning continents, will map hydrogen gas throughout cosmic voids. Current surveys only detect the brightest galaxies. SKA will reveal faint hydrogen clouds, collapsed objects, and gas flows that might fill supposedly empty voids. These observations will answer critical questions. Do voids contain significant hidden matter? How does void expansion vary with cosmic age? Are the largest voids truly larger than structure formation theory permits? While we cannot create cosmic-scale voids in laboratories, we can test whether vacuum energy varies under extreme conditions. Experiments at facilities like the Large Hadron Collider investigate whether quantum vacuum properties change under intense energy densities. If vacuum energy transitions are real, they should occur when energy density drops below specific thresholds. The Casimir effect, a quantum force between conducting plates in vacuum, provides another testing ground. Recent proposals suggest measuring the Casimir force in ultra-high vacuum chambers that simulate void-like conditions. Any deviation from predictions would indicate vacuum energy depends on environment. These experiments connect the largest structures in the cosmos to the smallest scales in physics. If cosmic voids truly represent different vacuum energy states, then quantum field theory requires modification. The implications would cascade through all of physics. How cosmic voids evolve determines the universe's ultimate fate. In standard cosmology with uniform dark energy, cosmic expansion accelerates eternally. Galaxies beyond our local group will eventually redshift beyond detection. In trillions of years, the observable universe will contain only our merged galaxy, surrounded by perfect darkness. But if dark energy's density increases with time, a possibility allowed by quintessence models, acceleration could intensify until space-time itself tears apart. This Big Rip scenario predicts that perhaps in 50 billion years, cosmic voids will expand so violently that they disrupt galaxy clusters, then solar systems, then molecules, then atoms. Alternatively, if dark energy represents a temporary phase, it might decay into ordinary matter or radiation. Voids would stop expanding faster than the cosmic average. Gravity might reassert dominance, potentially reversing cosmic expansion entirely in a big crunch. Recent breakthroughs suggest a fourth possibility. Cosmic voids might nucleate vacuum decay events. If our vacuum exists in a metastable state, like supercooled water that hasn't frozen, a quantum fluctuation in a cosmic void could trigger a catastrophic transition to a lower energy vacuum state. This would create an expanding bubble of new physics traveling at light speed, rewriting the laws of nature everywhere it passes. The universe wouldn't end. It would transform into something fundamentally different. Observations of void behavior over the next decade will determine which scenario is correct. We've journeyed through evidence revealing that the emptiest places in the universe aren't empty at all. They're filled with dark energy, quantum vacuum fluctuations, and possibly exotic matter we haven't yet detected. This forces a philosophical reckoning. What does nothing mean? Ancient Greek philosophers debated whether true void could exist. Aristotle argued that nature abhors a vacuum. Empty space was impossible. Modern physics vindicates this intuition. Quantum mechanics forbids truly empty space. Even in perfect vacuum, particle-antiparticle pairs continuously appear and vanish. But cosmic voids take this further. They suggest that the properties of empty space, its energy density, its expansion rate, perhaps even the strength of forces within it, vary throughout the universe. If true, we inhabit a cosmos where the laws of physics are local rather than universal. The fine-tuning that allows atoms, chemistry, and life might be just one configuration among many. In regions we call voids, different configurations prevail. The most profound implications emerge when we consider that our physics, measured and confirmed in our matter-filled cosmic neighborhood, might not apply in the vast emptiness between galaxy clusters.
We're like fish in a lake, trying to understand water by studying the lake bottom where we live. The deep, open water, the voids, might operate by entirely different principles. Every cosmological measurement we make assumes homogeneity, that the universe looks the same everywhere on large scales, but voids challenge this assumption. If 30% of space consists of underdense regions with different expansion rates, then our averaged measurements might not represent reality anywhere. We're averaging over diverse environments to get a mean that matches nowhere. Consider measuring the average depth of terrain by mixing ocean trenches and mountain peaks. The resulting number tells you nothing useful about either environment. Perhaps the same applies to cosmic measurements. This has practical consequences. When we measure the cosmic microwave background and conclude that the universe is flat, we're averaging over billions of light years containing countless voids and filaments. Does the universe's geometry actually vary locally? Are we flat only on average, while individual regions curve positively or negatively? Recent theoretical work suggests that void geometry might deviate from flatness. In 2022, physicists at the University of Geneva calculated that super-intense voids, regions where matter density drops below 1% of the cosmic average, should exhibit negative curvature. Space-time itself becomes saddle-shaped within these regions. If confirmed, this means we don't live in a single geometry universe. We live in a patchwork cosmos of varying geometries stitched together at void boundaries. Perhaps the deepest mystery involves life itself. We exist in a relatively dense region of the universe. Our galaxy resides in a filament connecting two massive galaxy clusters. We're not in a void, and for good reason. Voids contain few stars, few planets, few opportunities for chemistry complex enough to generate life. But why does the universe contain both dense regions where life can form and vast voids where it can't? Why not a uniform cosmos? One possibility: structure formation requires both. Gravity pulls matter together into galaxies only because voids push matter out of underdense regions. Without voids actively evacuating their contents, gravity alone might produce only weak clustering, never condensing matter enough to form stars. In this view, cosmic voids are necessary for our existence. The same dark energy that accelerates void expansion enables matter to collapse into galaxies elsewhere. The forces are two sides of one process. Another possibility emerges from multiverse theory. Perhaps our universe represents one possibility among countless others. In some universes, voids dominate and galaxies never form. In others, matter clusters uniformly with no voids. Only in universes with the right balance between matter clumping and void expansion can observers arise to ask these questions. This anthropic principle offers no mechanism, only pattern matching. Yet the pattern remains. We live in a cosmos precisely balanced between somethingness and nothingness, between structure and void. One final, speculative possibility. Cosmic voids display properties that seem computationally convenient. They're regions where detailed simulation becomes unnecessary: sparse matter, simple dynamics, faster expansion.
If the universe were a simulation, optimizing computational resources would require allocating most processing power to dense regions where complexity concentrates. Voids would be low-resolution regions, rendered in minimal detail, their contents simplified to basic expansion rules. This isn't serious scientific hypothesis, it's unfalsifiable speculation, but it captures something real about void properties. They're suspiciously simple given cosmic complexity elsewhere. They're blank spaces in the cosmic tapestry, as if something needs to conserve resources when drawing the universe. Whether this points to simulation or simply to fundamental limits on cosmic complexity remains unknown. We began this journey with a cold spot in the cosmic microwave background, an anomaly that shouldn't exist. We followed evidence through supervoids spanning billions of light years, through galaxies spinning too fast, through expansion rates that violate predictions. The evidence reveals that the largest structures in the universe challenge our deepest assumptions about cosmic architecture. Voids aren't empty regions where structure failed to form. They're active components of cosmic evolution, shaped by dark energy or modified gravity or vacuum transitions we don't yet understand. Current scientific consensus acknowledges that cosmic voids profoundly influence universal expansion, but whether they require new physics remains debated. The question will be answered by observations already underway: the Vera Rubin Observatory Survey, Euclid's dark energy measurements, and the square kilometer array's mapping of void contents. Within this decade, we'll know whether dark energy's properties vary spatially. We'll know whether the largest voids exceed what standard structure formation permits. We'll know whether we need to revise general relativity, quantum field theory, or both. But here's what we know now. The universe is not uniformly structured. We live in a cosmic web of matter filaments separated by vast emptiness. That emptiness acts, it pushes, it shapes, it might hold the key to ultimate cosmic fate. The gaps between structures might be more important than the structures themselves. The canvas matters as much as the painting. The universe is vast. The mysteries are endless. The journey continues. But remember this: sometimes the most profound truths hide not in what we can see, but in the vast expanses of what we cannot.
you.